Okay, thank you. Good morning, everyone. My name is Daniele Magazzini. I'm chairing this session on knowledge engineering and execution. We have one journal paper now and 2 papers for the main track. The first speaker is Torsten, talking about towards effective ASP planning.
Yes, thank you very much. So this is actually an abstract of a journal paper we've been publishing last year. And it describes more or less the adaptation of planning techniques to answer set programming. So I think before starting, actually, we owe a lot of ideas that we are very grateful to Jussi Rintan, actually from whom we adapted a lot of ideas. Now, so since it was actually a larger research program we've been doing, this talk will be very shallow and just pointing to things. Let's just dive right away into it, motivation. So actually what ASP what we are interested in here is more or less to learn about planning techniques that we can adapt in ASP, that we can model on a very high level. And this means we're not necessarily planning afterwards, but planning is a sub-problem of something that is a larger in a larger context. This can be, for instance, robotics in warehouses, logistic problems, multi-agent things, everything that you see here on the slide. And then what we decided is to say, okay, in order to also to compare actually how far we got with these techniques and when we adapt them, let's actually use PDDL also as benchmarks, which is actually not our original purpose of the whole thing, because as I said, we want to look rather at richer formalisms where we can actually draw on the knowledge representation capacities of ASP. So more or less the objective of the work was twofold. First of all, to try in how far can we transfer technology or techniques in automated planning to ASP. And of course, primarily, these are techniques that you find in CP planning or in SAT planning, because the approaches are very, very similar. And then the idea is, of course, once we did this, study the effect, actually, how far can they take us in ASP. Good, so and now perhaps for those of you who don't know what ASP stands for, it's answer set programming, right? Not that you think I'm talking about asynchronous server pages, because that still happens. Good, so this is more or less the usual planning workflow that you guys are all familiar with. You start from a PDDL specification, you give this specification to a planner, and you get a plan, right? So the way actually we are implementing this with ASP is that way. So we take the PDDL description and translate this actually in a set of facts. And then we have encodings, which are more or less specifications of planners that are then combined with a specific instance, and you get a plan out, and you get a plan. That's more or less how things work. It's important actually here that we do not compile things as you would do in SAT, right? That you compile the whole planning problem right away with all the semantics in a propositional formula. No, you compile this in facts, like a deductive data, a database or whatever, and then you have a separate thing for how the problem encoding as such works. You really separate, as in classical computer science, right? Where you have your data and you have your program. Okay, that's more or less, that's the standard setting. And what we also did is, because one technique we were interested in is actually what is the effect of preprocessing. So one feature of PLASP is actually that we use fast downward. And when we get an SAS specification, then actually we do the whole thing again. Actually, PLASP as such allows you to produce 2 formats, PDDL or SAS. Okay, that's more or less how the overall workflow works. And as I said, preprocessing is one of the techniques we were looking at, and the other one is actually the technique of parallel yet serializable plans put forward by Jussi Rintan a lot. So let's first look at how do we actually represent these plans. So, well, you all know that the planning problem has three major ingredients: the initial state, the goal state or the goal condition, and the actions, which are then defined in terms of preconditions and effects. Now, if we translate this to ASP effects, we do this in a very direct way. And actually, these semicolons here, you can read this as actually 5 facts: fluent of x1, fluent of x2, fluent of x. And this is real, true ASP code. I'm not cheating on you. You can copy and paste this and give it to the machine, right? So, and those of you who know Prolog or who know more or less how this works will be familiar with this format. Then you have here the initial situation, x1 to x5 are true at time point 0. In the goal, x4 and x5 must be true. And you have these 4 actions here. And there you have prec stands for the precondition of action A3, sorry. there's another precondition, and here's the post-condition. And these guys here actually are the values, right? So it's a multi-valued representation. You have a variable x2, it should have value 1. Okay? Good. So this is more or less how we take that's actually the file format, how we take PDDL description and then map them into facts, and that's the representation of the planning instance as such. Now let's look at again what we want to look at. So one thing is, of course, to find sequential plans, and here is such a plan. We have the initial situation, then we apply action A1, and these are the new values of the variable. This guy changes, this guy as well, and we get a sequential plan. I don't want to go too much in detail, just to recall a little bit what we are dealing with. This is the sequential plan. Then you can look at finding actually parallel plans that you can afterwards serialize into such a plan again. And the idea is, of course, when you have a parallel plan, your search space is more shallow, and that's more or less the idea of that. And there are different concepts for that. So this is actually the for all step plan defined by Riusi, where the idea is that each serialization must lead to a sequential plan. And that's actually here, for instance, here, then you can parallelize, and you only have to plan actually 3 steps instead of 4. That's already cool. And then there's the notion of exist step plans, where for each parallel plan, there has to exist a sequence of actions so that you get a serial plan out of this. And as you see here, this allows you to compact things even more. And there's still the relaxed exist plan, where actually you have a super parallel plan, which you can then serialize again. And I'm not going to detail that. This is just to give you a visual idea of what it is, because we won't have time for that. Okay, now let me show you our planner, right? It fits on one page. So the idea is more or less that we use reification, metaprogramming, that if a variable has a value at the beginning, it's reified, and it has this value at time point 0. And then we use incremental ASP solving, and you describe incrementality by having program fragments. This is the check. This condition is an integrity constraint. It makes sure that the query holds at the last time point. And this is always somewhat removed and put in for the last time point where you're checking currently. And then you have the transition function, which is again just a program block which you declare like this, and that's it actually. There's one thing missing on the next slide. So what this more or less means is, so each fluent has exactly one value at each time point. Each action may occur or may not occur. This checks the precondition. So if an action occurs, it cannot be that's the post condition. If an action occurs, it cannot be the case that the post condition does not hold. And then here we have two things that say, well, we detect actually when a variable changed its value, because it has another value at t minus 1 and t. So this guy changed its value, and if an action occurs, its effect must take place, and it cannot be the case that there is a change that has not been caused by an effect, right? It's a very vanilla encoding, and the reason why we wrote it up that way is you will see that it's very easy now to implement all these 5 possibilities that we've seen before on finding parallel plans. The first of all, vanilla planning, sequential planning. So we take this code and we append these 2 lines and we get a sequential planner, right? That's plain PDDL planning, which gives you serial plans. So this here just checks the precondition. So it must not be the case that an action occurs and its precondition does not hold at the previous condition. And this here is the sequentiality condition. So it cannot be the case that more than one action occur at a time point, right? And now you can more or less push the button and get a serial plan. And now again, I cannot go into details. This is now the common code to all these encodings. That's sequential planning. This is actually the code that you need to add for all step plans, where just a bit the idea here, this single here just says, oh, if there is an action and the pre and the post condition change, this is actually the variable we have to look at.
So the next speaker is Alfonso Gerevini. We'll be talking about compiling away PDD3 preferences.
Good morning. This work is a joint work with Francesco Percassi, and this part of his PhD thesis. Soft state trajectory constraints are a class of temporally extended goals that in PDDL3 are called preferences. Planning with preferences, plan quality depends on the preferences that are satisfied by the plan. because preferences have utilities or violation costs that have to be optimized. In this work, we study an approach to planning with preferences that is based on compiling them away. An important challenge here is to develop a compilation that is efficient, taking into account the current planners and the algorithms that will use it. We focus on qualitative preferences, the so-called qualitative preferences in PDDL3, which are preferences that do not involve numbers. The target language of the compilation is very simple, which is a plus because many planners can support our compilation. Basically, it is just strips with the action cost. There are several approaches based on compiling preferences. All these approaches basically are based on using, in some way, automata for representing the preferences and encoding these automata, and they encode these preferences in the planning states and in the operators. And they have different ways of synchronizing the automata and the planning states so that a preference is satisfied if and only if the automata goes to the acceptance state. In our approach, so there are different ways of doing this, and in the paper there is a description of the differences in detail with respect to our work. The major difference is that we do not use automata, but we compile directly the preferences into the operators. And this allows us to optimize the compilation by exploiting the structure of the operators. In this presentation, first I will briefly introduce planning with the soft state trajectory constraints or preferences. I will briefly describe our compilation and present some experimental results, and finally the concluding remarks. So what are these soft state trajectory constraints? We can illustrate them with a few very simple examples in the logistic domain. So for example, we might like to have that whenever a truck is at a location, the goods that the truck has to load from that location are already there, available for loading. Or that a truck should load the good A from depot 1 before good B from depot 2, or that every location with goods to load should be visited at most once by the plan. And we express this as a soft constraints. A strips plus problem, a strips problem with action cost and preferences is a tuple in which F is a set of fluents, I is the initial state, O is the set of strips actions, G is the usual set of goals, P is the set of preferences of soft state trajectory constraints, and C is the const function that assigns execution costs to the actions and violation costs to each of the preferences. Okay, more formally, this is these are the set of preferences that, or soft trajectory constraints that we consider in our work, which are the qualitative preferences of PDDL3. So briefly, let S0, S1, Sn, the state trajectory generated by a plan. At end phi is the usual goal. Always phi means that phi must be true in every state of the trajectory. Sometimes phi must be true in at least one state of the trajectory. Sometime after means that if phi is true in some state, then psi must be true in some other state after the state in which phi is true. Similarly for sometime before, if phi is true in a state, then psi must be true in a state before the state in which phi is true. At most once, phi must be can be true in at most one state of the straight trajectory constraints. And here, phi and psi are first order formula. So in this brief presentation, we'll focus the examples on the sometime before constraint. The compilation method is inspired by the method by Kaider and Gefner for compiling away soft goals. It has a similar structure, but many specific differences. In this approach, the state description is extended with some predicates, and the operators are extended with one precondition and a possibly empty set of conditional effects. We have two special actions for get, forgo, and collect for each preference, where collect P means represents the fact that the preference is satisfied in the plan, and forgo P represents that the preference is violated in the plan. Each solution is forced to be a sequence of 3 subplans. The first subplan pi prime contains only original operators and is used to achieve the hard goals of the problems. Then there is a special action ends that blocks the use of the original operators. And finally, this pi prime, which is a subplan formed by forget and collect actions only, and we have exactly one of these actions for each preference. Okay, a key ingredient in our compilation is the notion of operator preference interference that is automatically computed. So we have that an operator is a violator of a preference if it falsifies the preference, if the preference is false in every state that is generated by this operator, considering the prefix of the plan up to this operator. It is a threat if the preference could be falsified, could be false. It is a support if the operator is somehow useful to make the preference satisfied, and neutral if there is no interference. So the classification is done in an efficient way by checking particular conditions of the preference against the operator. And the formal definition of this condition is in the paper. So here let's see just a few examples to illustrate these concepts. So consider an operator O that has no precondition and just one effect, that is B. This operator is a violator for the preference always phi, where phi is not B and the A or C, because it makes phi false. It is a threat of the preference sometime before phi psi, because this operator can make phi true, because it depends on the state where it is applied. It is a support for the same preference if it can make psi true, because it can make if it makes psi true, this can be useful later if the plan will make phi true, because the constraints say that when phi is true, before psi was true, and neutral in the other case. So this is the compilation scheme restricted to some time before, just for simplicity. And the other constraints can be easily handled in a modular way by adding other elements to this schema. And in the rest of the talk, I will just illustrate two things. Well, one thing, the compilation of the operators, which is in the blue. Here in the blue line. Basically, each operator, original operator, is compiled by a function comp OP that adds one precondition and some conditional effects. Then we have these special action ends that I have already discussed, and the collect and forgo actions for every preference. So let's see this compilation function for an operator O. So basically, the compiled operator O prime is just has the same preconditions and the same effects of the original of the original operator, but in addition we have this precondition normal mode that is used to force the action to be only in the first part of the plan, and we have a possibly empty set of additional conditional effects, one subset for each preference. And this, now I'm going to illustrate this set of conditional effects that is WOP. Okay, so let's consider the preference sometime before phi psi and the operator O. Now, If O is a support of P, sorry, we add the first conditional effect that has effect phi sin. If it is a threat, we add the conditional effect, the second conditional effect that has effect P violated, and otherwise we do not modify the effects of the operator. So the conditions of these conditional effects says what we need to be true in the state where the operator is applied in order, in the first case, to be sure that phi is true, and in the second case, in order to be sure that P is violated. And in the first case, we record that the fact that we have seen phi true with this fluent psi sin. And in the second case, we record the fact that we have violated the preference with this fluent P violated. And the conditions of the conditional effects can be obtained by regressing the formula that we want to be true at the end of the operator through the operator. So far, the compilation is not yet strips. We have conditional effects and other features that are not strips. So we need to compile them away. Conditional effects could be crucial because in this compilation we might have many conditional effects. So it's important to have an efficient compilation of the conditional effects. And for this we have developed a specialized compilation that is an extension and optimization of an existing one by Nebel, the polynomial method. And it is optimized by considering the particular kind of conditional effects that we have. In particular, you have the conditional effects from different preferences and never interact. And this, together with another observation and other details that are in the paper, allows us to remove some of the actions that are in the compilation of the conditional effects of Bernard Nebel. And the other optimizations that are not specific for preferences and that we believe can be useful more in general for any kind of problem that has a conditional effects. We also have that other optimizations like the cost, some forgo actions can be removed and the cost of violating the preference can be given directly to the action that violated the preference, and other optimizations that I don't have the time to discuss. So let's go to the last part of the talk about the experimental results. So in this table summarizes an experiment in which we have compared the performance of several strips PLASP planners using our compilation and a state-of-the-art planner that is LP-RPGP that supports directly the qualitative preferences that we have considered in this work. As we can see, we have, these benchmarks are the benchmarks from the IPC5. We have 5 domains, 20 problems for each domain. The numbers here are IPC quality scores. And we can see that in 2 domains, the compilation approach is much better. In 1 domain, it is slightly worse, and in 2 domains, it's similar. Overall, it's very difficult to point to the right point. Overall, in the total column, we can see that Llama, a version of Llama that we consider performs quite better than LP-RPGP. We have also analyzed the percentage of the total cost of violating all the preferences in the plans generated by the planners, and here for each domain. In this plot, we have, for example, rovers, in which we can see that LP-RPGP, which is on the left of this picture, has a bar that is higher than the other ones, which means that violates many more preferences. And the colors here say the the different kind of the percentage of the different kind of preferences that are violated. So we have the green bar here is much larger for LP-RPGP, and this corresponds to the sometime before preferences that I have illustrated before. So that means that it performs particularly worse for this kind of preferences. We have also analyzed the performance for each type of constraints, and overall we have that compared to RPGP, our approach has a much better performance when we for compiled always at most once and sometime before preferences, similar performance for sometime preferences, and slightly worse performance for soft goals, where RPGP performs slightly better. Okay, here we have the table in which of the results, and we have to consider only 3 strips plus planners and only the sometime before preferences. And you can see that the gap is quite significant. If we see the total column, the IPC scores, the higher is the better. For Llama is 75.6, and for RPGP is only 45. For the soft goals, LP-RPGP works slightly better. This is the only class of constraints where the compilation is not yet as good as LP-RPGP. So to conclude, in this work, we have investigated a new compilation schema for propositional planning with qualitative PDDL3 soft trajectory constraints. A good thing of this compilation is the target language is very, very simple, and many planners can use it for free, so many planners can handle planning with the preferences without changing the code. And the approach so far, according to our experimental results, is quite competitive. There is still room for improvement for soft goals, and this, I have to say, this is the part of the compilation that we didn't touch because we used directly the compilation of Kaider and Geffner. And in future work, we want to do additional experiments, of course, and comparisons. We want to include in the compilation the constraints of PDDL3 that have numbers, such as old after T5, where T is a number, and others. And we would like also to consider the possibility of compiling more general LTL formulas that have some form of nesting, and so we go beyond PDDL3. Thank you.
Thank you. Questions?
Thanks, Alfonso. So there's one very particular property of the formulas in PDDL3, that is that when you convert them into automata, this automata for each state, so you can reach an accepting state in only one step, or one rejecting state in only one time step. So my intuition is that your approach kind of relies in this property, but maybe I'm wrong. So having said that, is your approach extrapolable, can be extrapolated into another class of LTL formulas that are more complex, for which, you know, the automata transformation of these LTL formulas gives automata that don't have this property that I just mentioned. Or let me rephrase the question. Your off-the-shelf approach can be extrapolated right away to other more complex goals that are not in the PDDL3 fragment? What is the property that needs to hold for a formula to be used with your approach?
Well, it's not easy to actually answer this question because I don't have in mind particular properties that we can that we could find in an automaton that represents an arbitrary preference or in an arbitrary RTL formula that allow us to say, okay, we can compile it in an efficient way. This is something that I really would like to understand better, because I believe that there are some conditions that allows us to generalize this approach to a larger class of LTL formulas. And I have some very preliminary ideas, but I cannot give you a positive answer at the moment.
Oh. Okay, we are running out of time, so let's thank Alfonso again. Next speaker is Niemueller, talking about goal reasoning in the CLIPS executive for integrated planning scale.
Thank you very much. Hello. This is joint work that I'm presenting with Till Hofmann and Gerhard Lakemeyer from RWTH Aachen University. I'm now with X, the Moonshot Factory, formerly Google X, but the work I'm presenting today has been completed and entirely conducted at the university for my PhD. So robots must achieve goals by completing tasks. That's kind of obvious, but planning is only 50% of the job. So it's kind of a shift gears from the two talks before, where we now focus a little bit more of what has to happen once we have the plan and we want to execute it, and how do we integrate this back with planning. Some key criteria there in robotics are then, of course, time-efficient planning, and time-efficient also meaning in the sense of the time that it takes to plan. We need robust execution so that we can account for failures, and we need the seamless integration between the two things. And here, I'm actually going to talk about the CLIPS Executive as one system that we developed that integrates these aspects in a mostly principled way, as you will see. So it's a framework to design a top-level behavioral component of a robotic system. It could be applicable to other systems, but we care about robots in this environment. It invokes and monitors planning systems, so it treats planning as kind of a service it invokes. And the execution model that we use is built on top of the planning model, so we extend the planning model a little bit. It separates concerns, and I'm particularly going to talk about this in the future, and it's based on the CLIPS rules engine. So that's our implementation environment in which we implement this. And then goal reasoning, which is the focus of this talk about this system, is monitoring of the actor's objectives or mission to keep the actor's commitments and goals in perspective. That's just a sentence copied from the planning and acting book. So that is really something that we want to achieve in this system. So let's go to goal reasoning straight away. So that's our goal representation. We explicitly represent these goals as part of our specification, but they're not only a logical formula that you can have for your planning system. There can be arbitrary goals. The system must just be able to interpret what these goals mean, and some of those might then boil down to be PDDL planning problems. On the right-hand side, you see the data structure that we use, and I'll go into a few details of those later on. Important to note here is they all have a unique ID, so each goal is unique, but then they also have a class, and that allows us to determine how we treat specific goals. One class could be a PDDL goal, and then we know, okay, we need to invoke PDDL planners for this kind of goal. And by this, we kind of generalize the goal concept for multiple kinds of goals, right? So we want to separate concerns in our system. So we have the domain and plan representation that's underlying everything that we do, but then we want to have something that is goal reasoning, and that tends to be highly domain specific, and we want to make it easy for the user to exchange that part of the system to adapt it for their domain. Then we also have action selection, and that might also depend on the kinds of plans that you have or on the kinds of domain you're working in. Action execution is actually one that we have standardized the most. There's coordination that needs to go on if you have competing resources or multiple robots acting in the same environment. The world model and state estimation can be domain independent, and some things you might be able to do generic. So you always see that I'm balancing these. We want to have some generality in the system, but we also want the user to give them the hooks to extend it as they need for their specific domain. So the goals that we have actually determine the overall top-level flow. And that's one of the key slides. So if you forget everything else about the talk, this slide is very important. This is based on work by Mac Roberts, who is sitting here in the back. So thanks, Mac, for doing all this work. What we've done is we took this idea of the goal lifecycle, but then stripped it down and cut away the things that we didn't need and that just complicated things. And then based on this, we extended what we were doing. And as I said, the goal drives the overall flow in our system, and that's done by the goal lifecycle. And it also helps us in separating the concerns within our system. So eventually what happens is if you pose a goal, it's just formulated, right? It sits there, you don't do anything with it just yet. It's just an option that you're considering. Then you need to choose among those goals. One thing that you can luckily see is that you have these gray and white boxes. The gray boxes are more or less when you need to take action in some sense, not only in the sense of acting in the real world. And the white boxes are choices, when you can actually choose something out of the options that you have, right? So we have now these goals that are formulated. Then the goal reasoner steps in, and that's now the domain-specific part, and selects the goals which it finds interesting, or which it could consider that it could be interesting. And then we expand those goals. This is where planning could come in, so we could plan for these goals, but it might also mean that we go to a plan library that we have built beforehand and then take those plans for execution. Once we have those plans, we actually need to commit to those goals, right? So now we can do another selection round or another choice and see, okay, we have these goals, which we have expanded, and we have plans for these goals, and now let's evaluate what of those is actually the best course of action given our actual mission that's encoded in the goal reasoning component. Once we commit to a goal, let's get dispatched, and that's now when we actually, in the robot kind of setting, go to the real world and need to actually task the robot with doing something in the real world. You see these crosses and check marks there. So after dispatching, either the plan will have succeeded or it will have failed. And then we can consider what that means for our plan. That's when evaluation comes in. So evaluation essentially means capturing effects of our goals that we could not encode in our underlying PDDL encoding. For example, think that some plan fails at some action within your plan. There's nothing in PDDL that tells you what effects does the failure have on your environment. And this is what we can do here in this goal evaluation step. We also account for explicit goal rejection, which is the left arc that you see right there. We often use a pattern that we call generate and filter. We generate all the goals which might be interesting, and then we filter out the ones which are less important or which actually are infeasible at the moment, and then we take the top priority goal out of those survivors of the goals. So how does that look when we have a couple of goals in parallel? So you see on the top the different goal modes that we had that I just showed in the goal lifecycle. Then in the 4 rows, we actually have the evolution of 4 independent goals. Don't get tricked that they are in the same kind of pattern under these modes. They might run in parallel, they might run one after the other, or even shifted slightly, right? So there's no time bias meant by this diagram. So on the top row, where it says 1 here, that's a goal. It gets formulated and selected, and then we expand it. And here actually is one feature that we can do is that we invoke multiple planners for one single goal, and then we get multiple plans for those goals. And then the commitment, where before it was just decide which goal to execute, also determines which of the plans for a specific goal we want to execute. Think of having metrics for some of those goals, and you might pick the one which is better in your current environment. Then you dispatch it, and in this case, some action fails, and then, can you see this? No. Some action fails, and then the overall goal fails, and we can reason about what that means for our world. The second goal is an easy one. We plan for the goal, but then for some reason we don't like the goal anymore, and we just reject it, and we're done with it, and it's retracted and removed. And next is leads over to the coming slide. There actually we do not expand a goal just into plans, but we expand a goal into sub-goals. Right, so here it's a one-off goal indicated by this V. So that means one of those 2 goals needs to succeed for the parent goal to succeed. So what happens here when you actually expand this goal here, we generate a new goal that gets expanded by itself. When we commit to this goal, this actually starts executing, and then eventually that goal succeeds. That happens here. It's propagated back to the parent goal, and then the parent goal succeeds. So that's another thing which is important about this approach when you do this goal reasoning part, is that you can actually compose goal trees out of the goals that you And that gives us the ability to exploit some knowledge you already have about the domain and put this in the goal tree in order to pre-structure the planning problem for the system that we have. Right? So for example, coming from the logistics league, planning the whole thing is pretty much often infeasible in the planning time that we have. But if we compartmentalize it a little bit and already give some hints by that to make the planning problem a little bit smaller, the overall planning problem becomes feasible. These parent goals actually can have different semantics. So that's actually an eye test for you, I think. So here on the top, we have a parent goal which must run one of these two goals below. Then the yellow one is an always reject goal, so we just reject it for the purpose of the demonstration. The one below that is a run all goal, so it actually says all of the sub-goals must execute successfully in order to deem the parent goal to be successful. And then there are a couple other semantics, run one, run all. We have a retry goal that gives you some ability to encapsulate retrying separately. And the right box here, that's actually one goal that has been expanded into a plan. So we can all represent this in one common tree. And that's actually a live visualization that you also get from the system when you run things that will automatically update and show you what's currently going on in the system, which is nice because you actually get to know what goals the robot is pursuing. And in case of rejection, you also get to know which goals the robot explicitly did not pursue and why. Okay, now how is planning now integrated? So how do we bring planning execution together? I already mentioned that we have as the underlying base model a PDDL domain. We use the exact same specification both for the planning system and also for the execution system. But what we do then is we actually extend the model that we have. For one, our world model, which is kind of the data that we have about the system, in our case on the execution side can also deal with numeric and geometric data. It can also have more complex data structures that gives us just more handle on the data that we see in the real world with the robot. The execution model then is a superset of the planner model, which is kind of the problem. And there, what we do is we enrich operator specifications also that we have in terms of, for example, sense predicates, where some predicates we actually have a sensor mode for. We can detect what that predicate means. If we finish an action, we do not just blindly assume this effect has happened, but we can actually verify after we have executed that action that this has happened, what we expected. And there are a couple of other extensions that we put into this model. So the planner integration works like this. We have the Eclipse executive, which has the exact same domain model, and the extended world model. We have the planner, which in our case is a plug-in to our system, that we feed the problem and read the plan back. The domain is the same, and in between we have something that we call the robot memory. It's essentially a structured database that supports the overall superset of we need, and that also provides us with automatic translations from, for example, geometric to symbolic models. So say you have the predicate that tells you the robot is in room A, but you only have a geometric position in your world model, then there's an automatic translation that has an additional map that allows us to make the mapping automatically from the geometric position towards what the planner needs in terms of symbolic representation. So we've integrated this with two kinds of planners, one with PDDL-based planners, and on the other hand, also with SMT-based planners. It works slightly different because it cannot take the PD domain directly, so we need to do some more translation work. But that's just to say that what we're doing does not only work for PDDL-based planning, but it can also be adapted to work with other modes of planning. Okay, action selection, so that's the next component we were concerned with. You don't need to read the rule in detail. It's just to say that that's the only change that we need to make to distinguish between sequential action selection, which means we treat a plan as a sequence of actions, and temporal execution. What happens on the on the left-hand side, for the sequential plan, we just say, pick the next action for which all previous actions have been done, and there's no other action with a lower ID or a higher priority. So then we can, by that we enforce this sequence of actions. And on the right-hand side, what we do is that for the executable actions, we just, executable meaning that the preconditions are fulfilled, we just check if the earliest start time has already passed and when it has passed, we execute it. That's kind of also the model that ROSPlan has implemented in the basic version, I think. So once we select those actions, and that's, again, one of the powers where this action selection you can actually make depending on the kind of goal. So you can have some goals that you execute sequentially, and you have kind of some other goals where you have plans that you execute in a concurrent manner. Now the actions that we have actually need to be executed, and that's kind of this state machine here that we have generalized to. So as you will see, the states are somewhat similar to the Go lifecycle because it just works so nicely for us. Initially, actions are formulated once we select them for execution, and the selection is the selection step that I showed just before. Those actions are pending. And then we have different execution engines within the executive that take care of different kinds of actions. Those will then take over, invoke the action, wait for it to be actually started, and then monitor the action, and eventually it will either succeed or fail. Since it's robotics, it will eventually fail at some point, but it's nothing we treat here, but we treat it on the Go level. If it succeeded, there come the sensed effects into account that I mentioned before. So if there are sensed effects, it might actually have to wait and see if it can actually observe the effect that it expected, and then it times out if it doesn't, and then it's a failure that we need to handle. Or on the other hand, if we can even say, don't wait for the sense predicates, just assume that went well and then just go on, because we know that there could be some actions afterwards that we first need to take, and then only wait for these predicates as preconditions of others. It also handles exogenous actions, which are actions that actually are triggered by systems outside of our control. That's often used to observe things in the environment, like we instructed a machine and we expect some feedback back. That's an exogenous action, that feedback back, and then we can wait for this here. Okay, so to conclude, we separate the concerns into individual modules and structured this by means of the Go lifecycle to have some handle also on the reasoning side and for execution monitoring what's going on in the system. The Go lifecycle also describes the goal progression, so how does the goal actually evolve in our system. And this has been used in the planning and execution competition last year and also in RoboCup this year, so I'm happy to say that my former team won this year's competition using the approach that I just presented. Thank you very much.
Thank you. Time for questions?
Thank you. Interesting. My question relates to the planner's models versus the execution model. Mm-hmm. And you have a mapping from the detailed metric execution model into some topological symbolic level. But in many cases, you need also the opposite mapping. Mm-hmm. In particular, when you have planned an action, you need to instantiate it.
Yes.
And then how do you do that? Do you do some sampling? In some case, you need to do that at the planning level, not only at the execution level. So that's my question.
So we're not doing this on the planning level because we rely on the symbolic planners as they are. We do this when we instantiate the action, when we parameterize those actions. Most of the time, what we actually get away with is that we have a fixed mapping between whatever the symbolic planner came up with into some specific coordinate, like we have a room, but then you have, actually have a topological navigation graph underlying or overlaying our map. And then those points map back to, by name, map back to things that you have on the symbolic level. And this is usually how we structure these things. So the navigation graph, that's how we call this topological graph, carries not all, but most of the information that we need for this in the physical setting information back. So it's something I didn't show here.
One last question.
Can you talk a bit about how you think about benchmarking these kinds of systems and any comparisons that you've done?
Yeah. So in the paper, we'll find some comparisons. What we did is we did this particularly in the realm of the logistics league. So we ran hundreds of simulations against other agents and then compared the outcome of these simulations, right? What we also did, but not with this system, but with the previous system that could be applied here too, is that we also do an in-depth evaluation of when and what the robots do in your environment at specific points in time. That also gives you, for example, an idea of how much time robots are wasting in certain places or certain situations, and that also gives you some performance indicators among these different approaches. Unfortunately, I don't know of a better way to have a more specific view on how to evaluate benchmarks, but we only treated them as situated systems and benchmarked them as a whole and try to have the most common ground within the base level system as we could get, so that we only exchange the one component on the top which does the execution or the planning.
Super quick question from me. Which kind of temporal planning do you handle? For example, concurrent action, deadlines?
Yes. So in this case, we used POPF for some of the plans, PDL 2.1, and when we got the plan back, we had a direct translation into our representation.
Okay, thank you. Let's thank again the speaker.